Okay, gang. Well, welcome to our fourth lecture. Really, I guess it's our fifth lecture, but it's our fourth full lecture. Today, what we're going to do is we are going to finish up sort of the background material for AI, the history of AI, and then we're going to take a look at the future of computing. I'm going to make a few predictions. We'll talk about that. For those of you who are interested, I like to say what my background is, as long as it holds out. This is my background from Space 1999, when 1999 was the far future. I'm speaking to you from Moonbase Alpha. So you'll see a lot of classic sci-fi backgrounds. And who knows? Maybe I'll pull out a few sci-fi backgrounds from this century. We'll have to see. Okay, so we had talked about last time. We had started talking about, well, last time we finished off the history, and then we decided that we were going to talk about 4 specific areas of progress over the last 10 years. And those areas are machine learning as it applies to machine translation. We covered that last time. And then natural language understanding. We talked about that last time. The 2 final areas that we wanted to talk about were computer vision and autonomous vehicles, basically self-driving cars, self-driving vehicles. So we're going to talk about those 2 things today. And then we're going to talk a little bit about the path forward, maybe, and then I'll talk about the sort of the future of computing. So before I get started, are there any questions that anyone has for me before we dive into things? By the way, the Turnitin is now up on Moodle. You should be able to submit your paper for similarity scores. Remember, you need a similarity score below 15% to get full credit. You can submit your paper multiple times, but after your 3rd submission, it'll start waiting 24 hours to give you your similarity score. So don't wait till the very end and submit it a bunch of times, because it will, after 3 submissions, it will start limiting you to a report once a day. So anyway, there didn't seem to be any questions, so let's dive into things. So computer vision. Well, to begin with, we already talked about Freddy. Remember, Freddy was the sad little camera computer looking at the board with a couple of items on it that took it 10 minutes to recognize a cup. Well, that was basically the early 1970s. But you might think, okay, well, was that the first approach to vision? And if so, why did they think it would be successful? And one way of answering that is to go back in time even further. If we go back in time to the 1960s, you will see an example of machine learning. They actually had perceptrons. That's what they were called, and perceptrons were a type of neural network. They were a type of neural network that that was only 1 layer deep. And so we'll look at these perceptrons. I wouldn't make a note. I know I hear some of you have your audio unmuted. Please make sure your audio is muted, because all 35 of us have to hear your background noises if you're not muted. Okay, so here's the video about perceptrons. And it'll give you some idea of what was happening in the early 1960s.
In the 1950s and 60s, scientists built a few working perceptrons, as these artificial brains were called. He's using it to explore the mysterious problem of how the brain learns. This perceptron is being trained to recognize the difference between males and females. It is something that all of us can do easily, but few of us can explain how. To get a computer to do this would involve working out many complex rules about faces and writing a computer program. But this perceptron was simply given lots and lots of examples, including some with unusual hairstyles. But when it comes to a people, the computer looks at facial features of hair outline and takes longer to learn what is told by Dr. Taylor. Cruikshank's wig also causes a little heart searching. After training on lots of examples, it's given new faces it has never seen and is able to successfully distinguish male from female, which it has learned.
Now, that's pretty friggin' impressive, okay? And that was back in the early 1960s. You can see it's in black and white. How do you reconcile what I showed you there, which was about 10 years earlier than Freddie, where Freddie was such a disaster? Well, one, you had still images, okay, so photographs in one, and in the other you had an object that was moving on a spinning board, right? So you could see the objects from different angles. So those are big differences. Another huge difference is that this perceptron was only learning two categories, male and female, right? And so it would classify every photo that it was presented as either male or female. So that's all it could recognize. But still, it was very, very impressive. And so that's why in the very early days, people were excited about machine learning until they figured out that it had problems they didn't know how to overcome. But in the early days, people were very excited about perceptrons and machine learning in general. So what happened? Well, what happened was, as we'll get to next week when we start talking about perceptrons in detail, and you'll learn the mathematics behind this and exactly what it means from a mathematical point of view. But it turns out that you can very easily prove that there are very simple problems that a perceptron neural network cannot learn. And so, Mike, give me an example. It can learn to tell whether two things are equal, but it can't learn to tell whether two things are not equal, if that makes sense. And we'll talk about that in detail. It can't handle an exclusive OR, to put it more in a computer science type thing. So the XOR perceptron by itself cannot compute an exclusive OR. So when they figured that out, people became disillusioned very rapidly, even though the perceptron in the early days was doing really, really cool stuff. So, well, two things. One is that particular piece of video is actually important to me personally. And one of the reasons why it's important to me personally is when I was a little kid, Walter Cronkite, who's an extremely famous journalist, did the nightly news, but he was also interested in science and space. The best coverage of the moon landings was Walter Cronkite. He actually, you can see, sort of breaks down into tears when we step foot on the moon. It's a very touching moment. But he also, like I said, was interested in science and technology, so he did a little Sunday morning TV series aimed mainly at kids. But it was like something you see on the Science Channel these days. And one of the things it talked about was machine learning, and it included that clip that I just played you. And I can remember seeing that when I was I don't know. I don't remember the age, 8, 7, maybe 10 or 12. I don't know. So I was a little kid. And I remember being so blown away by it. I was probably not 12. By then there were color TVs. But when I was a little kid, TVs were black and white. So it was probably when I was more like 8, maybe 9, maybe 7. But I saw it, and that stuck with me my whole life. I was like, it was one of the things that early on got me so interested in computers, the idea that you could teach a computer, you could teach it, and you could show it images, and it could recognize, men from women. And I'm like, wow, that was so super exciting. So that was, to me personally, that little clip of video is very important. But like I said, once people figured out that there were certain things that perceptrons couldn't do, they kind of abandoned machine learning. And the problem wasn't that people thought that neural networks would never work. In fact, that people had proved theoretically that anything you could do with a von Neumann machine, the typical computer that we have these days, you could do with a sufficiently advanced multi-level neural network. The problem is that to build such a network, you had to do all of the interconnections and weights between the neurons by hand. So it would be like, okay, I want to write a program, but I have to create a logic diagram for the special purpose machine that would do this particular task. And there would be many thousands, hundreds of thousands, millions of individual wires with weights on them that I would have to somehow come up with. And no one had any idea how you would do that. So theoretically, we knew that neural networks, multi-layer networks can solve problems, and we knew that for very, very simple neural networks, perceptrons, we could teach them. We had a learning algorithm for them, but we didn't know how to teach multi-level networks. And so it's kind of like, back to the underpants gnomes, we didn't have the middle step that you needed to be able to do anything really with it. So that's why they died out for a long time. But image classification, the problem that they were doing there has been around for a long time. As you see, it went all the way back to the very beginning. And there's a thing called ImageNet. ImageNet is a large collection of images, hundreds of thousands of images that humans have gone through and classified. So it might say, okay, this is a cup, this is a chair, this is a cat, and this is a dog. But instead of just saying what it's a dog, it would say what breed of dog it is. This is a German Shepherd, this is a Collie, this is a whatever. And so for about 10 years, starting in around 2010, there was a challenge that happened every year. It was called the ImageNet Large Scale Visual Recognition Challenge, the ILS VRC. So it was the Visual Recognition Challenge. Now they reduced. They had all the images, but they reduced the categories, the classifications, down to 1,000 different classifications. So in that little video I showed you, there were 2 classifications. Is it male? Is it female? Well, in the ImageNet challenges, there were 1,000 classifications, including 90 different breeds of dogs, if you can believe that. And there would be hundreds of images in each category. So if you had a poodle, you would have hundreds of images of poodles. And if you had German Shepherds, there'd be hundreds of images of German Shepherds. So if we go back about, well, not even 10 years, we go back like 9 years to 2011, about the best program that was out there had a 25% error rate. That means it would misclassify 1 in 4 images. And really, some of the competitors back then, entries into the challenge were as bad as 50% error rate. They get half the images wrong. But there was a big change in 2012, because before 2012, people had been using statistical machine learning strategies. They were machine learning, but they were statistical. And then in 2012, Google had the AlexNet, which was a neural network model that used what's called a convolutional neural network. Convolutional neural networks are multi-layer networks that can be trained, and that got a 15% error rate. In other words, it improved over the previous year's best submission by almost 10 points. And before that, you know, the best program would maybe be 1 or 2% better one year than the previous year's program. So to get, and it had been slowing down. And so to get a 10% jump in improvement in 1 year was just like crazy. And then over the next 5 or 6 years after that, the improvement was super dramatic. Let me come here and I'm going to share my notes so you can see this image here from my notes. This is the ImageNet competition results, okay? And you can see the error rate, 10%, 20%, 30%, 40%, 50%. And you can see back in 2011, as I was saying, the best one got about 25% error rate. So it would get 3 out of 4 images correctly. But the worst program there, you can see, was over 50%. It missed half of the images, okay? And these were, but these were like the 4 best programs in the competition that year. So don't think about this guy as like the worst of the worst of the worst. You know, anywhere in this range, say, you know, 30% was considered doing pretty darn good. Well, if you look at this cluster here in 2012, these are the programs that were using the old statistical methods. And here's AlexNet down here, way better than the best. See, down here around 15%. And then you look what happened over the next 4 or 5 years, right? In 2013, in 2014, in 2015, and then by 2016, 4 years ago, essentially every program in the competition, it was like 28 out of 30 or something like that, was getting about a 5% error rate. Now that means they're misclassifying 1 in 20 images. You might say, well, 1 in 20, that's still, you know, pretty crappy, isn't it, Mike? And I would say no, because that's actually much better than humans can do. And if you doubt me, can you recognize 90 different breeds of dogs? Maybe you can recognize 90 different breeds of dogs. Once we get past poodles and collies and little wiener dogs, whatever those are called, you know, Mike O'Neill is pretty much out of classification. So maybe I could recognize 5, you know. I absolutely no way in the world could recognize 90 different breeds of dogs. So it was doing, you know, back in 2016, it was doing much better. People were starting to write articles saying computers can now see better than people. No, computers could pass the ImageNet challenge better than people could. But that's very different, right? Because it's looking at still images there, and every image has to go into one of the 1,000 buckets that it knows. It doesn't know any other kind of buckets, all right? So even today, I mean, my data ended in 2016 there, but actually they ended the ImageNet competition then, and they've been working on doing a 3D competition these days, because by 2016, ImageNet was no longer relevant because basically every program using a convolutional neural network could do better than a person, so we weren't learning anything from ImageNet at that point. But that was a huge achievement. But I don't want you to think that vision is a solved problem, because it absolutely is not a solved problem. Computers do not see in the same way that people see. They're really classifying. They're not generalizing. The best way to think about it is a neural network that can recognize images, okay, that can quote see, and I put see in quotes, okay. Essentially what it can do is it can recognize the objects. Again, if every one of you could check to see that you're muted, that would be great. But like I was saying, the software can only recognize the images that it's been trained on. So one way of thinking about it, a human way of thinking about it, is the system is blind to everything except the objects it's been trained on. Now let's think about that. We're about to move over and start talking about autonomous vehicles here in just a moment, okay? But let's think about what I just said as it relates to autonomous vehicles. An autonomous vehicle can recognize cars and trucks from most angles that it's been trained on. If it sees a car flipped upside down and is looking at the bottom of a car, it might not recognize the car because, of course, it probably doesn't have a lot of images of the bottom sides of a car flipped over on its side, and you're looking at the undercarriage of the car sitting on the road. But it'll recognize cars in their normal positions. It'll recognize road signs. It'll recognize the lines on the highway. It'll recognize pedestrians. It'll recognize bicycles. It'll recognize motorcycles. Again, from all of the typical angles that you would have expected it to see. But if we go back to that car that's flipped over on its side, and we're looking at the undercarriage of the car, right? The car got flipped, and it's sitting on its side. Cars have a hard time sitting on the side, so maybe a big truck or 18-wheeler. That's invisible to the vision system. The vision system doesn't flag that as an object that it recognizes, so that object may as well not be there as far as the vision system is concerned, because it's not one of the objects that it's learned to recognize. That can obviously cause really big problems, and has caused really big problems, and has led to some deaths in autonomous vehicles. So why don't we move over to autonomous vehicles? I do see a question when I was talking about backpropagation, or I was talking about on neural networks. Yeah, we're going to use backpropagation for training when we get to those over the next few weeks. Okay, so autonomous vehicles. I have 3 video clips that I want to show you here, and they happen to be spaced pretty evenly, 20 years apart. And so this is a very good example of progress in AI, where we can look at the way that this particular field has evolved in the last since its inception, and we can look at it in 20-year intervals here. Okay, so the first thing I'm going to start with is something called the Stanford CART. The Stanford CART was a autonomous driving system that here is where it stood in 1979. I think is when this video clip was originally filmed. Okay, so So let me share my screen, and we want to show you this. Okay, the Stanford cart. This was state-of-the-art, 1979.
The problems of moving and seeing at the same time were even more taxing. At Stanford in the early 70s, Hans Moravec bravely tried to get his cart, a wagon connected to a massive computing engine, to cross a space avoiding objects in its path. Each flash represented 15 minutes of thinking time, which died the department's computers.
So the entire department's computers, every one of those flashes, 15 minutes.
Of the robot was accompanied by 15 minutes of computation, and the crossing of a large 30-meter room took 5 hours. A 4-year-old is already equipped with wonderful circuitry to look at the world and detect the presence of objects and to note the imminent collisions and to avoid them. So a 4-year-old can toddle across the room with apparent effortlessness. The Stanford cart used a hierarchy of programs which were anything but effortless.
So again, that's late 1970s. Well, actually, the 1970s in general. I said that was 79, but if you listen to the audio, it said during the 1970s. So all that work was taking place pretty much throughout the 70s. So even though that video was 79 at the end of the project, we'll say here, beginning in the early 1970s, we had the Stanford cart. Now, okay, that was pretty primitive, right? Like I said, you know, that video there, remember, every flash, you know, took 15 minutes. So it would move a little ways, take a bunch of photos, process for 15 minutes, move a little ways, take a bunch of photos, and, you know, that ain't, I mean, is it self-driving? Well, not at any speed that a human would put up with, right? But time works magic. So let's look at 20 years later. So from the early 70s, let's move in time to the early 90s. If I can do this quickly. Let's see if I can do it.
This vehicle is being
So now what I'm about to show you here is how far we had gotten by the early 90s. Okay, need to share my screen. Share your screen, Mike. Come on, where's your screen? Here we go. Okay. Carnegie Mellon University self-driving van.
This vehicle is being driven by a neural network. The network hasn't been programmed. It has learned by itself how to keep the vehicle on the road.
Recovering. Okay, very good. I won't try and go any faster. Earlier, we trained the network to imitate a person driving, having the network watch the person as the person drove along about a 500-meter stretch of road. Now the network has taken over for itself. You can see that down here at the bottom of the image, this square represents the image being fed into the neural network as input. The network has basically learned to key on the position of the white line and the edge of the road to determine where the road is and hence in what direction it should steer. All right. Here comes the shadow. This should be interesting. See how it deals with it. Doing okay. Yeah, things are going well.
While neural networks are superficially appealing, the tasks which nets can so far conquer are a far cry from common sense. This net has to be retrained if it rains.
Okay, so you see again early 1990s, and remember I said that neural network research never died off completely, but it was kind of it was kind of a backwater. people pretty much knew that you weren't going to be able to do a self-driving vehicle without neural networks, but they were still extremely primitive. I mean, that thing basically found the white line on the road and followed it, is essentially what it was doing. And it could only creep along, right, at, a couple of miles an hour, and it took a van filled with computing equipment to be able to do that in the early 90s. So that's about where things were. Now, things really began to change in the mid-2000s, about 15 years ago. DARPA launched what was called, DARPA has a series of grand challenges. So they launched a grand challenge in autonomous vehicles. The idea, remember, DARPA is the Defense Advanced Research Projects Agency. It's like the National Science Foundation for the military. And they fund a lot of projects that are very high risk, but they try to develop technologies that will be useful to the military and for civilians. I mean, the internet came out of ARPA. It was originally the ARPANET, and ARPA was essentially DARPA before they added a D in front of it, but it's the same organization. So the internet was created by the military, which some people find pretty amazing. And also Tor, right, that you use to like hide from the government and reassign your IP address and stuff like that. Guess who funded that? The NSA. It's a national security agency. So basically the government funds all of these technologies that hackers and people who are very much against the government have tended to adopt. I personally, regardless of how you feel about those issues, I personally find that humorous, as it were. But anyway, so in 2004, DARPA launched a grand challenge to be able to do a self-driving vehicle. So again, that would have been about 10 years after that video that I just showed you of the CMU self-driving van. It was a disaster, okay, in 2004. No vehicles finished it. The best vehicles, it was like a 150-mile course, and the best vehicle made it like 7 miles. Most of the vehicles didn't make it to the starting line, not the finish line. Most vehicles didn't make it to the starting line in 2004. But then in 2005, there was a huge amount of progress between 2004 and 2005. People got real busy. Stanford fielded a team. They had Stanley, and there was another big team from CMU. So, the usual suspects, MIT, Carnegie Mellon, Stanford, all were trying to show who's best. And Stanford won the challenge. In fact, Stanford's project was eventually bought by a company called Google, and that became the Google self-driving car project, all right, which is now running taxis in Chandler, Arizona. Chandler is a suburb of Phoenix, and so there are Google taxis running in Chandler. They don't have safety drivers in them anymore. They run on their own, and they seem to be doing well. But it's in a small geofenced area, so it's like in one suburb of Phoenix. But anyway, so let's look at. I'm going to show you a video now. It's actually about 8 years old, but it shows the promise, I think, of self-driving technology. So let's take a look at it. It's a real video. There's a safety driver in it. A little bit of it is I mean, it's really doing the driving, but as you'll see, it's edited a little bit to maybe make it look a little bit more capable than it actually was at the time. So let me get my video and let's share screen. And I'm going to share this. Okay. Some of you may have seen this, maybe not.
How are you? Just great. Where are you? I am driving. Where we go? Look, all no hands anywhere. No hands. No hands. I love it. So we're here at the stop sign. Yes. Cars using the radar, laser to check and make sure there's nothing coming either way. Like 5 lights on the old habits die hard, man. They don't die. Hey, anybody up for a taco? Yeah. What do you want to do today, Steve? I'm all tacos on myself. All right. Well, go get a taco at the drive-thru. And we're turning into this parking lot. Ow. No, it's kind of creep along here. Does anybody have any money? I've got money. No, I've got my wallet right here. You roll down your window and order a burrito. I'm doing very well. How are you today? This is some of the best driving I've ever done. 95% of my vision is gone. I'm well past the moonlight. You lose your timing in life, everything takes you much longer. There are some places that you cannot go, there are some things that you really cannot do. Where this would change my life is to give me the independence and the flexibility to go the places I both want to go and need to go when I need to do those things. Check it out. I've got quite the it's been nice, it's been nice.
So, first of all, how many of you had seen that video before? I see one person said that they remember that video. Honestly, it always still brings a tear to my eyes. I've seen it probably a dozen times that I've shown it in classes, maybe more. But, we think about self-driving as kind of it'll be a convenience when we have it, etc. But we don't think about the fact that that the ability to have something like that would dramatically change, would dramatically change some people's lives. As somebody who, I have certain vision problems. My vision's not that good, and I sometimes joke, that I'm in a race between my failing eyesight and technology to see which one wins first and wins the race. But no. And the other joke that I make, since I've got a Tesla, is I'm much better at driving than my Tesla, but my Tesla's much better at seeing than I am. There's a little bit of truth, maybe, to both of those things, but just a little bit. That's that was where the self-driving project stood in 2012. I would say that 5 years ago, I probably thought that we would have self-driving vehicles by 2020. If you had asked me 5 years ago, I would have said probably. If you ask me, will self-driving vehicles be common in 2025? No, I would probably say no now. That's 5 years away, but it's slowed way down. The progress has. You can solve 80% of the problem with 20% of the effort, but getting that final 20%, or especially getting that final 5% or that final 2% of the problem solved, just requires an extreme amount of effort. Now, Elon Musk still believes that he's going to have self-driving vehicles in a year or two, but he's been saying that now for about 5 years. So next year, right? But every fan of Elon Musk has learned to understand, Elon Musk time. Solving those last problems are hard, especially because if you're going to do a self-driving system, humans are going to demand that it be many times safer than a human. We accept that humans have accidents. We do not accept that our machines have accidents. And when one of our machines kills someone, we're out for blood from the machine. So for automated driving to be accepted, it will have to be many times safer than a human. 10 times safer, 100 times safer, I don't know what the number will be, but I do know that it will have to be safer. Okay, so that was automated driving. So what's the bottom line? Where do things stand now, and how do we go forward? What's the future going to look like? Well, no one really knows, but we can start, hypothesizing at least a little bit about how things might change. So one thing is very true. Over the last 10 years, especially over the last 5 years, progress in machine learning and big data have absolutely solved or nearly solved some problems that had been around in AI since the 1950s and that had been completely intractable. Clearly, we've made progress. Even though that 2012 video is a little bit, edited to make it look a little more powerful than it actually is, compare that, to 40 years earlier and the little cart that's trying to move across the room. So you can't say that there hasn't been tremendous progress. There has been. It's been huge progress, especially in computer vision and automated speech recognition and autonomous vehicles. It's just been huge progress. But certain fundamental problems from the 1950s still haven't been solved. There's no computer that can pass a Turing test. You cannot hold even the most basic conversations with a computer system. Now, yes, Google and the knowledge graph lets us hold teeny tiny conversations in very limited areas, but you can't. There's no computer system out there that can even understand a simple children's story. Okay, that's just beyond computers, and no one seems to have a good idea about how neural networks and learning algorithms can be applied to be able to solve that problem. So we know, right? We've made some progress. We know that we've got the way forward appears to be using neural networks, but no one knows how to get them to be able to do some very simple tasks like being able to understand a children's story, or being able to handle a conversation, even a simple conversation, being able to talk to a computer as if it were a 5-year-old. We just can't do that. Another problem is machine learning algorithms are essentially pattern matchers. They basically do recognition problems. Now, there are, you might say, Mike, you're being a little too narrow there because neural networks can play games and do things like that. And we just talked about GPT-3 on Tuesday. They're mainly what they do is pattern match. Another problem with them is that they can't explain how they generated a particular answer. So let's say some of you may have heard about Watson, IBM's Watson. Its claim to fame was about a decade ago. It won at Jeopardy. So the game show Jeopardy, a computer beat the best human on the planet, the best two humans on the planet playing that game. So Watson's been applied to a bunch of different areas like, disease diagnosis. So Watson might say something like, the patient has malignant pancreatic cancer. I'm 87% certain of this. But you can't ask Watson why. Why, Watson, do you think the patient is likely to have pancreatic cancer? There's no way for a system like that to explain itself. And that's problematic because if you're going to depend on computers to give you the answers to very important questions, you've got a military system and it says, urgent recommendation to President of the United States, launch ICBMs. If you ask it, why? And it says, because I say it's time to launch the ICBMs. That's not going to be a very useful system, I'm afraid. Or if you're, or again, let's say you're the unlucky person, the system says that you probably have pancreatic cancer, you're probably going to want to know, okay, how did you come up with that diagnosis? If just, you expect me to undergo chemotherapy or something like that? Well, how do I know that this is accurate? So that's a problem. Some people have begun referring to what neural networks can do as artificial autistics or artificial savants. And I was talking a little bit earlier when we were talking about vision. Are you really going to feel comfortable getting in a car when you know that it might plow into an overturned 18-wheeler because it's never been trained on enough examples of overturned 18-wheelers to recognize that that's an object in the middle of the road? The kind of mistake a human would never make. Now, balancing that, you've got to realize that, well, the automated driving car has cameras at 360 degrees around it, so it can see around the entire car. So even today, self-driving cars can avoid a lot of accidents that a human would have. And in fact, they fight back and forth about the statistics. Musk believes that he can show that you're much safer in a Tesla on autopilot if you're riding on a freeway or an interstate than you are if you have the autopilot off. But, it's statistics, and accidents are so rare that it takes many, many, many millions of miles of driving before you can begin to become comfortable with the statistics. Okay. So what's the way forward? There are two possible approaches. One way possibly forward is machine learning, either the biological neural network approach or the statistical approach. Beginning on Tuesday, we'll begin talking about the biological machine learning approach. I may say a few words at one point in the class about the statistical approach, but the emphasis is on the biological machine learning approach. The other possible approach is the classical, good old-fashioned AI approach, logic, algorithms, rule-based systems, those sorts of things. And that'll be saved for the last 3 or 4 weeks of the quarter. Maybe it's a combination of those two things. Certainly, at the present time, a lot of our systems are combinations of those things. But some people think that machine learning is going to be able to take over the whole enchilada. We'll have to see. Now, I want to talk to you about Doug Lennon. He is an adherent to the classical approach to AI, and one might consider him a scientist who's tilting at windmills, because he's been working on a project called Cyc, 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 for over 35 years, basically since 1984. And his project has been an attempt to teach computers common sense reasoning. By common sense reasoning, I mean the kinds of knowledge that any 5-year-old child possesses. Common sense knowledge about how the world works. So, for example, cups are held with the open end up, right? You're not going to hold a cup of coffee what we call upside down. The open end has to be up, or all the liquid falls out of it. After people die, they stay dead. That's a nice little fact to know. It's maybe an unfortunate fact, but it is something that you need to know if you want to understand, the world. So those are just two examples of common sense knowledge. And so I want to play. It's worth, I think, taking the time to play a little bit of video about this approach. And we're going to go back to that 1992 documentary that I've been using quite a bit this quarter. And we'll look at what it has to say about Cyc. So let me share my screen. I'm going to play two different clips from this video.
But computers made very bad students because they started out from such a low level.
Learning has the property that we learn at the fringe of what we already know. We learn that this new thing is similar to something we know already, and here's the difference. So the more you know, the more and more quickly you can learn. But the trouble is that we start our learning programs off with next to nothing. So they don't have a very big fringe, so they can't really learn very much very quickly.
But it wasn't hopeless. There was a way forward, albeit a rather audacious one. Leonard believed the only hope was to painstakingly feed the computer the millions of things it needed to know, so that it would be able to understand language and learn by itself. In 1984, he set up a project in Texas to do just this. Because it was likened to a vast encyclopedia project, it became known as Cyc. The task was, however, not to make an encyclopedia, but to input the kind of knowledge which is not in encyclopedias because it is too obvious to include. For example, Cyc would have to know some things no encyclopedia would dream of mentioning about Abraham Lincoln.
Dr. O'Neill, we can no longer see the video.
Okay. Did I lose my internet connection, or?
A Moodle pop-up is showing.
You can see me, yes?
Yes.
Or no, you can see me. Okay, so let's go back to this. You said the Moodle pop-up. Can you see the screen now?
Yes, we can. There was something saying like your session's about to end. But it's gone now.
That's okay. That's extremely weird. Okay. Well, we basically have gotten to basically what this is saying here. We'll go on to the next piece of the video. But basically, what that was saying was that you have to encode common sense. My favorite one is the thing about his children was always younger than he was and things like that. So let's see if I can get the video here to move forward. Try and get it to 50. Let's see. Sorry about this, guys. Hold on.
And Leonard thinks he has a good chance of success.
So you can see the video, yes, no?
As mankind's first foray into
Yes.
large-scale knowledge engineering. I originally put the chance of this project succeeding when we started at about 10%. I think even that was a little bit optimistic. I now put the chances at about 2/3, over 60%. And the reason why I'm a lot more optimistic now has to do with the ways in which we have overcome various tar pits, the potential thorns that might have snagged us along the way. There are all sorts of topics that we've had to deal with: time, space, causality, belief, emotions, rationality. And each one of them has had a whole community of researchers dedicating their life to formalizing, to studying, to codifying.
Leonard and his team, who call themselves cyclists, are hard at work trying to capture the world piece by piece, trying to build a mind which knows enough so that it can understand language and learn.
And how you was transported. Okay. That's logical. So here is her house, and this is walking to her car.
Psych was having some success handling ambiguous phrases.
As another example, we could have something like Mary read Melville, where you can't obviously read a person, but since Melville wrote some novels like Moby Dick, and since author of has high metaphor sensibility, the system knows that often you say an author's name like Shakespeare or Melville when you mean something written by them. And so down here it says probably what you meant is that Mary Shepard was reading the Moby Dick novel.
It's a profession type, and nurses are medical.
Building a mind is painstaking work. What comes to mind when you think of a nurse? Psych's mind has to be filled with all of these details of what a nurse does. Taking temperatures, giving medicines,
And what about stress in a job? Stress in a job. I mean, nursing is very stressful. Yeah. I guess this is after a lot of time burnout.
For Psych to be able to understand stories about nurses, it must know about pressures on the job, and even the fact that most nurses are female. Even though Psych runs on these computers, it has no body at all. It is just software, a pure mind. What does an entity with no body make of all the knowledge that it is fed of a world it has not directly experienced? At night, while the rest of the team are asleep in bed, Psych looks for inconsistencies in its database and comes up with new generalizations. And it's clear that Psych sees the world in a pretty novel way.
So in the morning we come in and see what inconsistencies it's found, and we also sometimes see what interesting new discoveries it's made. This is very interesting. I wonder if this is true. This one says that two countries that have pretty much the same mixture of religions are members of pretty much the same international organization. So I'm going to put a question mark next to that. Here's another funny skewing based on what happens to be in the knowledge base. This basically says that most people are prominent. And that's because most of the people that we put in, aside from ourselves working on the system, are famous people from history. This is actually another funny sort of misunderstanding, where it's been told about Fred while he was shaving in the morning. And it's reached a kind of subtle problem where, on the one hand, it's decided that Fred, while he's holding the razor in his hand, has some electrical parts. But on the other hand, it believes that people don't have, in general, electrical parts. So it's trying to ask something here like, is Fred still a person while he's shaving?
Listening to Psych, one gets the feeling not of a developing child, but an alien intelligence who knows a lot that has a bizarre view of the world. But what would psych have to achieve to convince skeptics like Dreyfus it was really intelligent?
I would say if the Psych Project could understand stories of the sort that 4-year-old children could
So I think we'll leave that there. That gives you a pretty good idea of psych, and what it was, and again what it still is. That's a project that's still in business all of these years later. Now, back in the 90s, you know, there was a lot of excitement about psych. I personally was very excited about it. I sent one of my graduate students to Austin to work on psych on a summer assistantship, and you know, and I followed it quite closely. I still follow it. Why hasn't it changed the world? Well, the problem, as we will begin to see, I think, when we cover logic, is one, logical systems, I like to call them that they're doing reasoning without understanding. That's one thing, but Linnet believes that with enough data, it will reach understanding. The problem is the systems are very, very brittle. If you leave out one important fact that you need in a chain of reasoning, then the chain of reasoning breaks down. And so, you know, you might say, oh, well, I can just go in and patch it by adding that one fact. Yeah, that's right, but you soon turns out that if half of the time that you ask psych a question, you discover, oh, it's missing another piece of data, and you patch that in, and you know, you would think that, well, over time, there'll be fewer and fewer little patches that I have to put in place. But you know, but sometimes it almost, I mean, the project's been going on for 35 years. They haven't had success. So it's almost like every time they put in one patch, they discover that they need two more, right? And so many people believe that it's absolutely doomed to failure. It's a very old-fashioned approach to a project. These days we would say, oh, you need to crowdsource it. But the problem with trying to crowdsource it is that essentially all of that information is represented in a very highly technical language called cycle, which is basically you're writing things in a logic-based language. And so you notice when he was talking about, you know, Mary read Melville, he said, well, author of has high metaphor sensibility, you know, to that phrase he used there, high metaphor sensibility, is a string that represents a relationship. And all the system is doing is matching those strings. So you get back to the conversation that we listened in on from the Google talk, right, where you know, where we were going on with the Chinese room example was going on about the fact that, you know, programming is simply syntactic, that there is no semantics. And the argument is that no matter how complex the syntax and the syntactic processing is that you'll never get down to the semantics. So, you know, a lot of people believe that, you know, that psych will probably die when Linnet does, and it'll still be no closer to having solved the problem. I see some people saying that it's not a very efficient process. They should find a way to optimize the process. Like I said, the approach that he's using is very last century. It's not crowdsourced. They've attempted to crowdsource things like WordNet and add in additional knowledge bases, but it's just proven a lot harder than you would think. Now, I'm glad I didn't devote my life to psych, right? But I'm glad somebody has, because we'll if you never try, it's like the SETI project, right? If you don't listen to for the aliens, you'll never hear if they're out there. So I'm glad we're doing it. Doesn't mean that I think he's going to be successful. I would like you guys to read an article. I have it linked in the notes. It's from Wired Magazine 2016, so it's really not that old, 4 years ago. And it's called One Genius's Lonely Crusade to Teach a Computer Common Sense. It is about Doug Lenat. And 2016, remember, we were already well into the revolution going on with neural networks in 2016. So it's basically saying, hey, here's this other approach. And the article itself does a really good job. I've talked about the classical, good old-fashioned symbolic approach to AI versus machine learning. That article does a very good job of summarizing those two schools of thought. So I highly encourage you to read the article. Who knows? I might pull a question on the midterm from it. The other approach is the machine learning approach, and I would probably point to Ray Kurzweil's How to Create a Mind. It's a book he wrote in 2012 that I read. It's a pretty good book. He believes that all you need are pattern matchers, and that right now our neural networks basically do low-level pattern matching, but that when combined into a hierarchy that nobody knows how to build, and when taught with algorithms that no one knows, that you will end up with a mind essentially built out of arrangements, collections of neural nets arranged into hierarchies. That's his approach. Ray is an engineer at Google, and so he actually only came on to Google relatively recently. He had spent his entire career as basically at his own companies that he would start up and create. But Sergey Brin talked him into coming over to Google, because basically Sergey Brin said, come to Google and you can play, and we'll give you all the resources and people you need to explore your ideas, and that'll be a lot more efficient than you starting up yet another company. And I guess they waived a paycheck that was huge enough for Kurzweil to say, okay, I'll do it. So that's what he's been doing for the last 5 or 6 years. Most AI researchers, I would say, are somewhere in the middle, where they think that practical systems need to be a combination of the classical approach and the logical approach. So with that, let me take any questions we might have, because I'm about to launch into chapter 15, which is the last chapter of my text, the past, present, and future of computing. So before I do that, are there any questions anybody would like to throw up in chat real quick before I move on? I'm going to take a swig of water. Oh, my water bottle is invisible. This is fantastic. But it's only invisible when it's not moving. That's pretty cool. How popular is the idea of AGI being made of AI subsystems? I see it in fiction quite often. I think that's almost any system. Take Google, for example, Google Home, or Google Assistant. We already talked about the subsystems that it's divided into, right? The automated speech recognition front end, the knowledge graph midware, that's actually implemented using logic, where the first is where the automatic speech recognition is machine learning, and then the back end of the system where it's text to speech, which is again another neural network. So yes, the AGI systems, I don't think anybody thinks that. Let me not say that. I think most people would say that yes, an artificial general intelligence would be composed of subsystems, discrete subsystems. Maybe not. And why do I say maybe not? maybe uploading will become popular or become possible. Uploading, where basically you map the connectome, all of your neurons and the synapses between those neurons to a computer substrate, and you simulate the firing between them, or you emulate the firing of those neurons. If that's the case, we might be able to build an artificial general intelligence that is essentially a copy of a person in silicon. And if we do that, we might have an AGI but have no understanding of how the AGI actually works, because all we did was we took a human brain and we made an electronic copy of that brain. Some people think that that may be how we reach an AGI. So, okay, so what about the past, present, and future? Read the chapter. The two things we've been talking about Kurzweil here. Kurzweil predicts human level AGI by 2029. It's only 9 years from now. He's been making this prediction since at least the 1990s. And when he first made the prediction, it seemed ridiculous. Now, the idea that in 10 years we could have a computer that could pass the Turing test doesn't seem ridiculous at all. If you look at the evolving nature of computing, we've all heard of Moore's law, right? Moore's law, people interpret it to mean, okay, that computers double in processing speed every X years, every year and a half, every 2 years, every 3 years, something like that. Its actual formulation was a little bit more narrow and technical. It was basically that the number of transistors on a piece of silicon could be doubled every 2 years. And so that was Gordon Moore, still alive, the co-founder of Intel. You might have heard of that small little company. They make chips, right? So Moore noticed that really back in the 60s. And it's been going on for a long, long time, over most of my life. Over almost all my life, people have been saying it's going to come to an end. Some people claim Moore's law has already come to an end, and that progress is slowing down. I think it is. I think it is clear that progress is slowing down some right now. Okay. And if you look at a very narrow definition of Moore's law, well, it's definitely coming to an end, because now we're down to single digit nanometers as the width of the size of features that we can put on a silicon chip. They're down to the range of single digit nanometers. And the problem is that at that size, if you get, it's already, quantum tunneling is already starting to be a problem. Basically, electrons can jump between wires or between features when they shouldn't be able to do that. But we're getting small enough that quantum effects are starting to interfere with our chips. And so they're not gonna, the features are not going to get much smaller in size. So some people believe that that means that silicon, additional progress in silicon is dead. We'll talk about that for in a moment. But anyway, Kurzweil predicts that we would have human level AGI by 2029. If you depending on the model that you use, okay, you need about 1 exaflop. So in other words, 1 billion floating point operations per second to be able to simulate a human brain's activity in real time. Okay, what does that mean? Well, basically Kurzweil says a flop, a floating point operation, is the lowest level of computation in a computer system. And then he asks, well, what's the lowest level of computation in a human brain? And that is a neurochemical transmitter crossing one synaptic gap. Now, you've got billions of neurons in your brain, and they each have thousands, tens of thousands of interconnections between synaptic gaps between those neurons. Neurochemical transmitters move very, 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 very slow compared to electrons in a computer, but the brain is massively parallel, right? So if you say one flop is equivalent to, in a very crude way, is equivalent to one firing of a cell across a synapse, right? One little communication happening between two brain cells. Then you come up with, you need between 1 and 10 billion flops per second to be able to simulate what's going on in our brain. So how close are we to 1 billion flops? Well, if Moore's Law hadn't slowed down, we would have had that this year, okay? If you go back in time and you look at the exponential curve, 2020 is when we should have gotten a billion flops. That's called an exaflop, 10 to the 18. We don't have an exaflop right now. The fastest computer right now is about 40% of an exaflop. It's 415 petaflops as of June of this year. The Chinese have it. That's their supercomputer. But the U.S. has 2 exaflop level supercomputers, one's that Argonne National Labs that's supposed to come online before the end of next year, before the end of 2021. And I believe the Chinese have one that they're working on as well. So it's pretty much, we're going to have an exaflop supercomputer next year. Okay. So 1 to 10 exaflops is the raw power, according to Kurzweil, of the human brain. So, you know, things double about every 2 years or so, but even conservatively like that, and if the conservative estimate is 10, you still end up getting to, we pretty much have the hardware now, according to Kurzweil, to do whole brain emulation. We got another decade ahead of us before 2029, right? And we probably will have 10 exaflops before 2029 if things keep going, because even though we're getting near the end, things haven't stopped as far as Moore's Law is concerned. So that's where we stand with that. Kurzweil also predicts, Kurzweil predicts that we'll have human-level intelligence in a supercomputer by 2029. By 2029. How did he come up with that? Long ago, back in the 1990s, he used Moore's Law to compute when we would have the raw processing power to emulate a human brain, okay? And that came out to be somewhere between 2020 and 2030. So he gave himself some wiggle room and said 2029, before 2030. So by the end of 2029, human level AGI. We should have the hardware to do it anywhere between now and a decade from now. And he felt like once we had the hardware, we would figure out the software to be able to do it. So that's where that prediction originally came from. And the Moore's Law part of it has stayed pretty much, for 30 years, has stayed pretty much on track. We now have a supercomputer. We will next year have a supercomputer that can do an exaflop. Not bad to be off by 1 year for a prediction you made 30 years ago. When people looked at what he was saying, yeah, you're crazy. You're talking silly talk. So what's his current silly talk? Well, his current silly talk is that he's also been saying since the 1990s, and that's by 2045, the singularity will occur. Basically what he did there is he said, well, if you have human level intelligence by 2030, then things will double every 2 years. So by 2032, computers will be twice as fast and blah, blah, blah. And you know how the doubling goes, right? After 10 doublings, right, you have something that's 1,000 times, 1,000 times. So if it's 2 years, you know, to do a doubling, then you should have supercomputers being 1,000 times smarter than humans around, you know, the 2040, 2050, sometime in that time frame. And basically Kurzweil says, well, computers are 1,000 times smarter than we are. There's no way that humans will remain the dominant intellectual force. And remember, if we get human level intelligence in a supercomputer by 2030, it only takes about 15 years for the power of a supercomputer to go down to, you know, a personal level computer, whatever that'll look like. And so basically by the 2040s, your laptop or your cell phone or smartphone or God, whatever we're going to call it, should be as smart as you. And that's just the phone itself. And then when you connect into the cloud, right, you know, you should have access to AIs that are, you know, thousands of times more powerful than we are. So anyway, so that's the singularity prediction there. We talked about Moore's Law. Someone asked, what's a flop? A flop is a floating point operation per second, flops. Okay. So we'll have an exascale supercomputer next year that ought to be capable of doing whole brain simulation. Another technology that's going on that's getting better exponentially is the level that we can scan at. So you know we have MRIs, right? Magnetic resonance imagers, and the pictures that those can take are getting, the resolution is getting better and better and better every year, essentially on an exponential curve. And so again, if you look at the trends, by about 2030, you should be able to start to get synaptic level scans of brains. And so that's essentially, Kurzweil's looked at that, and if the trends hold, it's like, well, we'll have the raw computing power and we'll have the scanning power to scan a brain, so we ought to be able to emulate it. Anyway, so that's where that comes from. Okay, so we're about to jump into visions of future past, because I love sci-fi and I love to see how things have gone. Let me take a moment to look at some of the comments, see if there's anything else I need to speak about. Someone mentions, Brendan mentions Sophia. That's David Hansen Robotics. He's very into creating lifelike, very lifelike androids, I guess you'd call it, mainly android heads. But while I really like the work of David Hansen and would love to get him on campus as an ACM speaker for us, he's kind of a showman. He's very good at building robotic heads that move realistically, but unfortunately, a lot of people think that they are intelligent, and they are not. He just puts chatbots basically to them, and most of the interviews that have been had with are carefully scripted to make the robot appear intelligent, that are absolutely not intelligent at all. And then there's someone asking about quantum computing and Shor's algorithm, and hold your horses on that. We'll get to it if I don't run out of time, which I probably will. Okay, so visions of future past. It's tough to make predictions about the future. Sorry, I blew that. It's tough to make predictions, especially about the future. Yogi Berra is known for saying that. Also, oh gosh, the physicist's name is just escaping me, but it's a funny statement, but it's very true. It's tough to make predictions about the future. Why? Well, because when you get things right, people don't give you credit because they go, oh, that was obvious, right? And then when you get things wrong, people laugh at you and go, well, you missed this obvious thing. So it's a thankless task trying to predict the future, because if you get it right, people don't appreciate it, and if you get it wrong, people laugh at you. That hasn't stopped people from trying to predict the future ever since, I guess, Nostradamus, probably before that. So let's look at what people in the 1960s thought that computing would be like in the year 2000 and beyond. I ask that as you watch this video, that you forgive its sexism, because it is blatantly sexist. They did a much better job of predicting what the technology would be like than predicting what societal norms would be like 40 years later. So don't laugh too hard.
Fingertip shopping will be one of the many homemakers' conveniences. This video console will be channeled into the store of your choice. There, a camera will scan a display of wares, which she will select by push button. Another part of this console is the household monitor screen. It maintains a watch on critical areas in the house, swimming pool, or yard. What the wife selects on her console will be paid for by the husband at his counterpart console. All bills and transactions will be carried out electronically. A central bank computer will debit the family's account the amount of purchases and credit the department store, for example, forming the family's home computer at the same time. Father, at the touch of a button, receives an instantaneous printed copy of his budget, the amount of taxes he owes, the payments left on the car, and so forth. All documents and household records are available on the video screen for immediate reference. Also at his disposal is an electronic correspondence machine, or home post office, which allows for instant written communication between individuals anywhere in the world. To maintain these and hundreds of complex electronic circuits, a monitor checks all circuits every few seconds, inserts a backup circuit if and when trouble develops, and alerts the communal service agency for replacement.
Okay, so that gives you an idea of what people were thinking that the future would be like. Okay, now now again, you guys are making my point for me here. As you guys laugh y'all's asses off, right, and say, oh, spy on the family. Basically, the internet will just be a bunch of webcams. You know, but look at what they are predicting there. They're predicting that you'll be able to shop from home, right? Now, yeah, it's the 1960s, dude. You know, there was no internet. There was no, you know, television was brand new. So the idea that, you know, okay, there's a camera in the store that takes pictures of the stuff. Okay, but the idea that you could shop online, the idea that you would pay for things electronically, the idea that you would access your bank electronically, that you would have a printer, that you could send email. Yeah, he wrote it out by hand, but the ideas are all right. You know, the actual technology that they predicted, you know, isn't that great. Now, the thing that they got most wrong, I will agree with Alex on this. The internet is a series of tubes. Okay, they completely missed that part. But why did they say that? Because back in the 60s, computers had vacuum tubes in them, and televisions did too, by the way, and that was the electronic device most people were familiar with in their home. Those tubes would fail, and you would have to call out a television repairman to come and swap out tubes in your TV set. These days, if your TV set breaks, you buy a new one, right? There aren't people who come out and repair them. But back in the day, televisions were very expensive. They were worth, by today's dollars, $5,000 or $10,000 for a TV set. And if a tube would go out, you'd call the TV repairman. He would come out and he would find out what tube was broken, and he would replace it. So that's what they were talking about there. Okay, so a few of you are being nice and saying that they nailed it. Right, okay. Now, I think the big takeaway was that they couldn't comprehend modern graphics and the advent of the mouse. That's a very good thing to say there, Jonathan. I like that. And that's right, they couldn't, okay? Okay. Now, let's look at another video. This one was created in 1987, I think, or 88. It's called Knowledge Navigator. It's a video by Apple Computer that was made about 3 years after the very first Macintosh computer was made available, okay? The very first Macintosh computer couldn't do anything other than have the little mouse that you could move icons on the screen. And what do I mean by you couldn't do anything? Trying to create a four-page document, okay, with text and graphics was about the limit of what that thing could do. Okay, so it was black and white, of course, right? It wasn't black and white. It was on or off. So there was no shades of gray. It was on or off. Okay, so it was extremely primitive. But here's where they thought computing would be today. So they were looking 30 to 40 years into the future and saying, what will computing be like in the late 2010s, okay? So 2015 to 2020. What will computing look like then? And this is what they came up with. Now, as you watch this, you're going to obviously think about what they got wrong, but I want you guys, why don't you type in chat as you watch this thing, the things that they got right, okay? And let's see if you guys can see what they got right. Again, this was created in 1987. Okay.
You got 3 messages. Dirk
undergraduate research team in Guatemala, just checking in. Robert Jordan, a second semester junior, requesting a second extension on his term paper. And your mother reminding you about your father's
Surprise birthday party next Sunday.
Today, you have a faculty lunch at 12 o'clock. You need to take Kathy to the airport by 2. You have a lecture at 4:15 on deforestation in the Amazon rainforest.
Right. Let me see the lecture notes from last semester. No, that's not enough. I need to review more recent literature. Pull up all the new articles I haven't read yet.
Journal articles only.
Fine.
Your friend Jill Gilbert has published an article about deforestation in the Amazon and its effects on rainfall in the sub-Sahara. It also covers drought's effect on food production in Africa and increasing imports of food.
Contact Jill.
I'm sorry, she's not available right now. I left a message that you would call.
Okay. Let's see. There's an article about 5 years ago. Dr. Flemson or something. He really disagreed with the direction of Jill's research.
John Fleming of Uppsala University. He published in the Journal of Earth Science of July 20 of 2006.
Yes, that's it. He was challenging Jill's projection of the amount of carbon dioxide being released to the atmosphere through deforestation. I'd like to recheck his figures.
Here is the rate of deforestation he predicted.
What happened? It was really off. Get me the University Research Network. Show only universities with geography nodes. Show Brazil. Copy the last 30 years at this location at 1 month intervals.
Excuse me, Jill Gilbert is calling back.
Great. Put her through.
Hi, Mike. What's up?
Jill, thanks for getting back to me. Well, I guess that new grant of yours hasn't dampened your literary abilities. Rumor has it that you just put out the definitive article on deforestation.
Aha. Is this one of your typical last-minute panics for lecture material?
No. That's not until,
4:15.
Well, it's about the effects that reducing the size of the Amazon rainforest can have outside of Brazil. I was wondering, it's not really necessary, but
Yes.
It would be great if you were available to make a few comments. Nothing formal. After my talk, you would come up on the big screen, discuss your article, and then answer some questions from the class.
And bail you out again? Well, I think I could squeeze that in. You know, I have a simulation that shows the spread of the Sahara over the last 20 years. Here, let me show you.
Nice. Very nice. I've got some maps of the Amazon area during the same time. Let's put these together.
Great. I'd like to have a copy of that for myself.
What happens if we bring down the logging rate to 100,000 acres per year? Interesting. I can definitely use this. Thanks for your time, Jill. I really appreciate it.
No problem. But next time I'm in Berkeley, you're buying the dinner.
Dinner, right.
See ya, 4:15.
Bye-bye.
While you were busy, your mother called again to remind you to pick up the birthday cake.
Fine. Print this article before I go.
Now printing.
Okay, I'm going to lunch now. If Kathy calls, I'll be there at 2 o'clock. Also, find out if I can set up a meeting tomorrow morning with Tom Lee.
Enjoy your lunch. Hello, Professor Bradford is away at the moment. Would you like to leave a message?
Michael, this is your mother. I know that you're there. I'm just calling to remind you.
So was kind of cute. Let's see what you guys picked up on. Let's see that there was a lot of 44 messages. A sister that can summarize his mom said, yeah. Let's see. Okay. Visualizations, FaceTime, looks like Zoom, touch screens, touchscreen tablets, exactly. That was complete science fiction. Yeah, it's a Mac because it looks like a Mac. Messaging and voice recognition, something like Google Assistant, tablets with folding screens. Again, none of that existed, okay? What are some of the things it looks like you guys missed? Oh, the fact that he was using wireless networking, the fact that, you know, that you could just, you know, that printers were hooked into the network. I really loved the little cards, right? We don't have those, but we have thumb drives. They're exactly the same thing. I actually wish we had gotten the credit cards. They look a lot cooler. But yeah, being able to do just, you know, all sorts of things. Now, what did they get wrong? Well, the assistant in the box. We don't have an assistant in the box. And some things look a little antiquated. The idea that you would use the telephone, that was the way people used the telephone back in the 1980s and 90s. These days, we mainly use email or we text, right? I don't, it's very seldom that I will call someone, just call them with a request. Frequently, if it's a request that I need some information and it's not time critical, I'll send an email. If it's something that's more time critical, I will text, right? And usually in a text, I'll say, hey, do you have a minute? I'd like, if it's something that I don't want in text, I want to talk. It's like, hey, do you have a minute? You know, or get back in touch with me when you can have a call. And so I almost never call someone just out of the blue. And used to, that's what people did all the time. Now, I don't know about your generation, but do you guys just call people? No, I doubt it. You probably text, right? Rarely. Exactly. Mom and dad, maybe the grandparents, people who aren't really connected, you might have to. My mom passed away a few years ago, but yes, I had to call mom because she didn't do email and she didn't text. And so it's like, well, if I want to talk to her, I'm going to have to actually talk to her. So anyway, okay. Let's see. We're almost out of time, so I'm going to skip the You Will commercials, which are really good. Actually, I can't skip the You Will commercials. I'm going to play them. This may drag on a little bit into the beginning of Tuesday's lecture, but I don't care. I'm having fun, and I think this is good stuff. So, in the 1990s, AT&T wanted to show what life in the early 21st century would be like, and they came up with a bunch of commercials. They were called the You Will commercials, and they're narrated by Tom Selleck. And I think this is 2 minutes well spent.
Have you ever borrowed a book from thousands of miles away, across the country, without stopping for directions?
Now, you have to understand how important that is, because before GPS and electronic maps, okay, it was the standard thing, you know, of asking for directions. And the standing joke was no man wanted to ask for directions because that was admitting he was lost. But anyway.
101.
Or send someone a fax. From the beach, You Will. And the company that'll bring it to you, AT&T.
Well, AT&T wasn't the company that will bring this to us. And no, we don't fax anymore, but sent an email. right?
Have you ever paid a toll without slowing down?
Okay. These days, no one stops for tolls anymore. There are scanners. You get a little thing on your car, and you just drive right through it, read your license plate. But in the 1990s, that's not the way you do it. When you got on a toll, you had to have exact change, and you had to throw it in the bucket, and so it was a giant mess.
Bought concert tickets from a cash machine. Or tucked your baby in from a phone booth. You will. And the company that'll bring it to you, AT&T.
Now, the weird thing about that is phone booths, which, what are phone booths, right? Well, before everybody carried a phone with them, there were phone booths. And the idea of buying tickets from a cash machine, well, you do that from your phone, but the idea of ordering those things electronically it's pretty close to what we ended up doing.
Have you ever opened doors with the sound of your voice?
Too easy to fake it.
Carried your medical history in your wallet. Otherwise, it's going to be just fine.
Green Clinic, I got a thing today or yesterday, and they've got an online portal that all my medical records are on. So it's not on a card, but it's usually in the cloud now.
So this is where we said the atrium.
Or attended a meeting. Like the kind of you doing in your bare feet.
Don't ask me if I'm wearing shoes right now.
You will. And the company that'll bring it to you, AT&T. Have you ever watched the movie you wanted to the minute you wanted to?
Now, you look at that and you go, okay, big deal. Netflix was not anything anyone had ever thought about. And then when Netflix did come about, for its first decade, it was DVDs that were in the mail. And also notice the TV set is a 16:9 flat screen TV. Those did not exist when this was created.
You wanted to the minute you wanted to. Learn special things. That's all taken from jazz. Now, any questions from faraway places? Okay.
So where does jazz come from?
Good question.
Well, I'm not teaching you about jazz. I'm not teaching you about computer science. But and they didn't predict a pandemic, but essentially online learning.
Tuck your baby in from a phone booth.
There they are with that phone booth.
You will. And the company that'll bring it to you, AT&T.
So, AT&T wasn't.
Have you ever borrowed a book
Oh,
from thousands of miles away across the country?
sorry about that. That was all pretty effing impressive. Okay. Pretty effing impressive. So it is possible to make predictions and sometimes get them right. So hold on. So sometimes people are able to get predictions that are really pretty close, and it's actually fairly impressive when they do. So that's sort of visions of a future past. I think I am, although I planned on finishing this up today. I think what we'll do is I'll begin class on Tuesday, and we'll talk. I'll try to keep it down to no more than 30 minutes, maybe even less. We'll talk about some of the promising technologies that are out there. Basically, I don't think that Moore's Law is really coming to an end. Broadly speaking, I think that the doubling of computing power is going to continue, and I'll talk a little bit about why I believe that next time. And then I'm going to take a look at some of my past predictions that I made, because I've been teaching material like this since the mid-1990s, and so I'd like to make my own predictions, and I've been doing this long enough that either my predictions should have come true, some of them, or they should show what an idiot I am. And so we'll go through a few of those, and then I'll go through some predictions I wrote 5 years ago for the next 10 to 15 years. We can see how I'm doing, and then a couple of long-term predictions. So that'll be fun. Like I said, I'm going to try not to take up too much time on Tuesday, but I don't want to cut that material out. It's kind of interesting, I think. So that's what we'll do next time. Are there any questions before we call it a day? I'll be happy to hang around after class if someone wants to ask questions. Okay, so I think what I'll do is we will, I'll stop the recording. If you want to stick around and ask some questions, that's great, but I'm going to stop the recording. So I'll see you guys on Tuesday. Have a good weekend.